We are going to study unconformities. Here we are going to see the definition and the different types of unconformities. The subject is important in structural geology, sedimentology and in stratigraphy. So, in these books you will find chapters on unconformity. So, let us start with the definition. What is an unconformity? It is a break in a stratigraphic sequence. And it records a major time gap and is caused by erosion or non-deposition. We have to understand the meaning of many of these words that are used in the definition. The word sequence, in fact, when we describe sequence stratigraphy, will be explained in details. A major time gap has been referred, but what is the exact meaning of major was classically not clear in the definition. Is it millions of years or thousands of years? However, we will see in the course of this presentation that some quantification has been made regarding the time gap, and it is caused by erosion, which is a well understood geological term, or non-deposition. Note this word or, this is not erosion and non-deposition. So, either erosion or non-deposition for a significant geological time can lead to an unconformity in the stratigraphic record. Let us get into the different types of unconformities, and then these words, the meaning of these words will be more and more clear. We start with the angular unconformity. Here we can think of an unconformity surface. AU stands for angular unconformity. Below angular unconformity, the layers are at an angle to the unconformity surface, and above the angular unconformity there can be near horizontal layers. So, if we think different lithological units A, B, C, D and E, and say here we have got F, G and H. From such an angular unconformity, we can comment about the geological events that have happened. Now, this angular unconformity, this sketch we are watching on a vertical rock section. This is important. We are not going to see such angular unconformity in horizontal section. We are looking at vertical section or subvertical section or near vertical section of the lithostratigraphic record. Initially, there were horizontal deposition of units. So, on the basement, this is the basement, layer A got deposited, then layer B got deposited, then C, then D and then E. Now, imagine from this deposition there was a tilting event, so that this lithological package A, B, C, D, E got tilted. So, here is the after tilting. E, D, C, B and A. Imagine an erosion takes place, that means these tilted units got exposed for a profound time on the earth's surface and the rock materials here got eroded and they went away. So, what remains is that something like this: E, D, C, B and A. In the next phase, new deposition happens. Layer F got deposited, then maybe the rock unit G got deposited and then the rock unit H got deposited. So, in this way a geological event is deciphered. I repeat, there was deposition of layer A, then B, C, D, E, they got tilted and then erosion happened and this defines the angular unconformity. We can call this surface as an unconformity surface or also just as an unconformity. And in other words, we can also say this line, which is a plane in 3 dimension, as angular unconformity surface or simply angular unconformity. So, the sequence of deposition that we decipher from this will be A, B, C, D, E, then angular unconformity and then F, G and H, and here we can put the arrow of younging direction, which means old to young. This way deposition has happened. Now, this tilting that I have described can also be produced due to a folding event. For example, imagine these are the different layers that got deposited, say layer P, Q and R, and due to a tectonic reason it got folded. Fold geometry can vary, but I am just drawing an antiform here, P, Q and R, and erosion takes place like this. All the materials, rock materials above this red line got eroded. So, what the appearance will be? So, here is R, Q and P, here is P, this is Q and this is R. And after that deposition has happened, layer X and layer Y has come into picture. So, this is one possibility how the angular unconformity can be produced. I have drawn from horizontal layers which got folded, then there was erosion and then there was deposition. So, this is the sequence of events which has taken place. Instead of antiformal folding, there can be synformal folding also possible in nature. For example, from here if I draw P, Q and R are the 3 layers. Now, we can again think of that there is an erosion took place and over that we can think of deposition. So, the folding can be antiform or synform, and a deformation followed by erosion and then new deposition will lead to an angular unconformity. In the textbooks you may find a picture like this, or you can find a picture like this or sketches like them, but let me tell you that it is also possible that this product will be folded once again or tilted once again. We apply a compression in this way, in horizontal compaction. What will happen? Layer PQR will be refolded, more tightly folded, and layer XY will be less folded. So, the geometry can look like this. The product will look something like this. If you apply a compression, layer PQR which is already folded gets more tightly folded, and layer X and Y get less folded. So, this is a case of folded angular unconformity. As I am showing that the angular unconformity, or for that matter any unconformity, can get affected by folding or structural deformation, angular unconformity or other unconformity can also very much get affected by faulting. Complications are possible. For example, in this case, say everything got tilted, one tilting event, then what will happen? This angular unconformity, say it gets tilted, so this geometry will be possible. I have explained previously for this situation what is the succession. A very simple question to the students: if these are the different units, in this case write down the succession just like this. It is an erosional unconformity U for unconformity. It is an erosional unconformity above massive plutonic rocks. What is the meaning of the word plutonic rock? These are the igneous rocks which crystallize at great depth, which has bigger crystal sizes due to slow cooling rate. We can write another type of unconformity known as disconformity. It is a type of unconformity in which beds above and below are parallel to each other. It is a type of unconformity where beds above and below are parallel, means parallel to each other. A paraconformity this is a case where a sequence of strata may be overlain by a set of parallel strata of much younger age and without a surface of erosion separating the two sets of strata. Let us draw the non-conformity. Consider that there is some plutonic igneous rock and over that an erosional unconformity, this one. So, we call it the non-conformity. and over that has deposition of sediments. This essentially means that the plutonic rock was exposed to the surface by some mechanism, and over that sediment has been deposited. Now, let us take the case of disconformity. Here this is the erosional surface, and imagine that there are some horizontal layers, and then in these depressions maybe some conglomeratic clasts are there, and over that horizontal sedimentation has taken place, P and Q. So, as we see, as per the definition, it is a type of unconformity where beds above and below are parallel. The contact between A and B is parallel to the contact between P and Q, or we can write the contact between B and C, which is below the unconformity surface, below the disconformity surface, D dash is parallel to the contact between P and Q. These are, as per the diagram, below the unconformity or below the disconformity, below the, and these are above the disconformity. Now, let us take the definition of the paraconformity. It says that there are strata and there are edge differences between them, but there is no surface of erosion in between. A paraconformity it will look like this: layer A, layer B and layer M, and this contact is the paraconformity. So, here the paraconformity is drawn in this sketch as a straight line, no irregularity, no erosion is marked. The big question is, in vertical section, how do we recognize then the paraconformity? For example, why not the AB contact is not a paraconformity, or above M layer, let us say layer N is there, M and N contact, why not that one is also paraconformity? How do we distinguish paraconformity? How do we recognize, and where do we expect in the geological context? There are two questions. Question number 1, how to recognize, and number 2, where paraconformities are formed, how they are formed, genesis becomes a question. Now, recognition of paraconformity is tricky. Now, this question, how to recognize, becomes very easy in case of a non-conformity, because one can identify a gabbro in the field which is a plutonic rock, coarse grains, and over that sediments are deposited and an erosional surface can also be seen. In case of a disconformity, we can see an erosional surface in between, and therefore identifying disconformity or at least as an unconformity will be possible. This is not the case with the paraconformities, where you see that this contact is not showing any undulations or any irregularities. The recognition of paraconformity can be most evident if one goes for geochronologic dating. Suppose the rocks are dated, rock M and rock B are dated, and a significant time gap is found, then we can think that the contact between M and B can be a paraconformity. But the geochronological dating technique is time taking, and in the field it is not possible to use. Is there any way to recognize the para-conformity in the field? The answer is yes, based on fossils. Let us think any species evolution, and I am making a very sketchy description. With time, the species morphology becomes more and more complicated. I am just representing in this way a simple morphology and then a complex morphology, then more complex morphology, and then much more complex morphology, and then extremely complex morphology. We do not have any species where exactly this geometry of morphology will be there, but I am just drawing so that to explain that the complexity in the morphology in species increase with time. This has been recognized for many species. Now, suppose from some stratigraphic cross section such an evolution of fossils have been identified for some specific species. And now, going to the field, one observes that in layer A that particular species is found, and in layer B same species with different morphology is found, but now we were expecting in M this morphology, but it has not come. Straightway there is a jump and this morphology has come. So, this means what? Here between B and M there was a time gap in deposition. Since there was a time gap in deposition, so no fossils of these two categories were deposited and were preserved, and therefore jump has been noted. So, based on this jump in the field, but this needs paleontological knowledge of identifying species, at least the morphology of the species can be taken into consideration. Let us summarize so far what we have seen. We have introduced the term unconformity and we have defined it. Here is the definition. The different types of unconformities, angular unconformity was described, how it appears in a vertical section has been shown, different possible ways of formation, tilting, erosion and sedimentation, or from horizontal layer a folding and then an erosion and then horizontal deposition, and this folding can be antiform or synform. This has been demonstrated. An angular unconformity can be horizontal, but everything can be tilted. So, this can be a field appearance. A non-conformity, disconformity and para-conformity have also been defined. In case of para-conformity, there is no erosional layer seen in between. The way to identify can be geochronologic dating, but that is time taking, and the other way to do is using the fossils, but that needs some paleontological training. We have discussed so far the different kinds of unconformities in terms of sketches. Now, we are going to see unconformities in field and in seismic images. To start with the angular unconformity, which was classically studied by Hutton at the Seeker Point in Scotland, we have two dominant litho units, the early Silurian folded turbiditic sandstones at the bottom, and these rocks are folded. We can see some of the folding evidences over there. Basically, we are talking about this package. If I call it A is here, and then late Devonian subhorizontal red sandstones. This is the unit B. So, below unit B, the lithologies are making an angle, and above this angular unconformity which is tilted, the lithologies are parallel. There is also an age gap, early Silurian which is at A and late Devonian which is in B. When we study the geological time scale, we will be explaining the terms Devonian and Silurian. For the time being, just remember that here A is the older rock and B is the younger rock. Turbiditic sandstone, turbidites are basically mud rich material in the sandstone which indicates deep water deposition and tranquil condition, whereas the red sandstone, the red color unit, mostly indicates that the environment of deposition over here was arid. So, there is a difference in paleo environment in which A and B got deposited. We will now see angular unconformity in the seismic image. The example is given from the South Viking Graben from offshore UK. This is the uninterpreted image. And this is the interpreted image. We can see series of faults. So, these are the normal faults, and we do not see these faults at the top of this layer. Angular unconformity. Note that over it the layers are almost horizontal, gently folded and horizontal. So, from the seismic image we decipher an angular unconformity. Let us look at the paraconformity. Here the Marshall paraconformity is shown by this line. We note that below this line the layers are almost horizontal and so also over it. So, there is no truncation relationship. Moving to non-conformity, in the seismic image we find that below this non-conformity and above it there is no angular relationship. Above and below the non-conformity, this is above and that is below, no angular relationship is found amongst the rocks, and the layers looks like above the non-conformity are almost parallel with the non-conformity surface. Let us look at a case of disconformity from the southern Gulf of California. Here L1 represents the disconformity. L1 line is over here. Look at the definition of disconformity and try to recollect. That is how the disconformity will appear in the seismic images. Let us look at the breakup unconformity, which I did not describe in terms of sketches. We can do directly from the seismic image. It is a geological feature, it is an unconformity that marks the transition from a period of continental rifting, continental crust getting separated, rifted, and to the formation of a new ocean basin. So, how it will be represented? It represents an erosional surface separating older syn rift, that means rift related sedimentary rocks, from the younger post rift sediments. So, it says that a breakup unconformity will have in its bottom the syn rift sediment and above it post rift sediments. Post rift sediment means that the rifting got over, deformation is no more happening, faulting has stopped, and then sediments got deposited. So, we will expect the post rift sediments will be structurally undisturbed. Whereas the syn rift sediments, we are expecting them to be structurally disturbed. The yellow line shown over here, which I can track, represents the breakup unconformity. Below it we are observing normal faults, structurally disturbed, syn rift sediment. Sedimentation was happening when rifting was going on. So, the structures that were generating the rift that also affect the sediments, and in this case they are the normal faults in this particular case. And above the breakup unconformity, we are observing structureless features, only the bedding planes. Here I can clearly see they are warped, but this warping is because of this uneven geometry. It is not a secondary folding, not a secondary folding. There is another view from here. This time I am marking the breakup unconformity by a black line. Above it there are layers which are less deformed, warped, but below it we can clearly see that the interpreter has marked normal faults. Indeed, we can see the movement of the marker layer. These two examples are coming from the offshore Krishna Godavari basin. This is the southern Indian portion, and this is Sri Lanka, and within this box, this place we are talking, that is the Krishna river, that is Pennar river, and within this red line is a seismic section. Since this is the geographic north, so this direction is southeast and this direction is northwest. So here you see southeast direction tallying with this direction and northwest direction is over there. Let us look at another term, drowning unconformity. It is a type of unconformity that represents a transition from shallow water, and this shallow water can be carbonate rich. Not all carbonates indicate shallow water, but through other studies we can establish that these carbonates are indicating shallow water, and transition to deeper water environment. The deeper water environments can be characterized by shales where slow rate of deposition of fine particles happen, and also the turbidites. Now, these drowning unconformities are associated with relative sea level rise. If we try to look at the drowning unconformity in terms of the terms that we have already defined, well, they can be paraconformities, disconformities, or angular unconformities. That means, if this is the drowning unconformity, there can be an angular relation between the material at the bottom and the top, or such as the case of paraconformities. This term becomes important when we study sequence stratigraphy. So, by seismic image we can find out the pattern of the layers, whether it is an angular unconformity, whether it is a paraconformity, but whether it is carbonate rich indicating shallow water, or whether it is a deep water deposit at the bottom of that unconformity cannot be worked out based on seismic image. Therefore, for these conclusions actual sampling is required. Only when the sampling has been done and their shallow water and deep water origin has been worked out, then only we can use the term drowning unconformity. Otherwise, we have to be happy using the term angular unconformity or say paraconformity.